Today, we are going to talk about probability of error in BPSK, binary phase shift key. In the data transmission in digital communication, where very important point of discussing the signal where it is modulated binary 1 and binary 0 through phase shift keying, binary phase shift keying. So that is where we represent the signal vector here as if that any signal vector representation, first of all, S1 of t, the signal vector as a cos 2 pi fct with a carrier frequency of fc. Then we can write it as root of a square cos 2 pi fct. So this is nothing but the power which is equal to half is a square. So power is half a square. So power is nothing but energy per time. So B is energy per time. So this is energy equal to half a square into time, t, duration of the symbol or bit of signal. Okay, this is where we get it as the P equal to energy to EB by T, half a square. So this can be written as root 2 EB by TB cos 2 pi fct. The signal vector A cos 2 pi fct can be written as root 2 EB by TB cos 2 pi fct during the bit period 0 to T or TB. So if at all we split this signal vector is root EB into phi 1 of t. Phi 1 of t is the orthonormal basis function taken as root 2 by TB cos 2 pi fct. So this is what the carrier signal at Fc, orthonormal base function. We multiply any energy of the bit, binary 1 or binary 0, plus root EB or minus root EB accordingly. So in general, the signal vector is represented in a n-dimensional as orthonormal base functions having n-dimensional, n orthonormal basis function, j equal to 1 to n. So in the signal vector, phi 1 of t, phi 2 of t, phi 3 of t, etc., phi n of t, the Si of t is the signal vector with their coefficients along with their orthonormal basis functions. So this is what Si of t is represented sigma Sij pi j of t for I equal to 1 to m during 0 to t. Similarly, this signal vector, if at all, we would like to observe the probability of error in binary phase shift keying. So that is being modulated at 180 degrees out of phase between binary 1 and binary 0. You can modulate phase at 0 for binary 1 and 180 degrees out of phase for binary 0 or vice versa. That is any phase that you can modulate, but the 180 degrees out of phase between binary 1 and binary 0. If you observe the space diagram, the orthonormal base function in generalized n-dimensional orthonormal signal vector, n-dimensional signal vector, one dimension is sufficient. So this is 0 phase and 180 degrees out of phase. This is what R is in 0. So binary 1, S1 of t is taken, for example, root EB energy. For binary 0, the S2 of t at the energy minus root EB, that is 180 degrees out of phase. So S1 of t is S11, Phi1 of t is a single dimension. S2 of t for binary 0, S21, Phi1 of t in another vector with a single dimension. So S1 of t, S2 of t represented accordingly phi1 of t as root 2 by tb cos 2 pi epsilon. This is what signal representation of BPSK. Now the equivalent distance between these two signal vector root tb and minus root tb to root tb is the equivalent distance dik, where r d12 the equivalent distance between these two signal vector. So the signals already modulated were binary 1 with a 0 phase and as binary 0 at a pi phase. They were taken as minus of this. And now this is the what the space diagram represented. dik is 2 root EB between region 1 and region 2. Now the binary 1 S1 or binary 1 is transmitted as long as that is received vector is lying in the Z1 region. Threshold is 0 between bisection of this S1 and S2. So there is no error. If the received vector lying here, whenever S1 is transmitted lying beyond the boundary, then there is a possibility of error because of that much of noise is added here. So this is what signal vector, and this is what the noise vector, and this is what resultant the resultant vector. So this is where lying in the other region, then only you will get the probability of error. Similarly, vice versa. So the BPSK, which can be generated just by multiplying with orthonormal base function of any binary 1 or binary 0 converted into root EB or minus root EB plus or minus, that is being multiplied with orthonormal base function, it is generated. Now the probability of error mainly concerned on receiver. So this is the correlator just by multiplying with the orthonormal base function and integrating over the period of 0 to tb. This is the x of t phi 1 of t dt 0 to tb. So this element, when orthonormal base function is we are multiplying, we will get root EB or minus root EB plus or minus. So as per the boundary of threshold 0, if it is lying above 0, that is being x1, which is s1, and binary 1. If boundary is the threshold is less than 0, then the threshold is 0, the received signal vector less than 0, that means negative. We can choose binary 0 accordingly as we assume that is x1 is less than 0. So that is S2. So this is what the signal, if binary 1 is transmitted, if at all we get the negative value less than 0, then in the decision making, we get binary 0. So that is error. Similarly, vice versa. So now the probability of error we estimate based on the probability density function of a random variable of x dx, where the signal vector and noise vector is the received vector. So because of the random noise, random variable, Gaussian variable, the signal plus random Gaussian variable, so the received vector is also Gaussian type. So that is why, so half the equivalent distance towards infinity, we integrate the probability density function of the received vector x, then we get the probability of error. So the probability density function of Gaussian random variable f(x) when 0 is transmitted, So that is where that is, you can take it as 2 pi sigma square e power minus x minus mu square by 2 sigma square. This is what the probability density function. So where the sigma square is n naught by 2, variance of noise is n naught by 2. If you substitute here 2 pi sigma square 1 by pi n naught root pi n naught e power minus 2 n naught by 2, that is 1 by n naught x minus mu square. So here for binary 0, so that mu, that is mean, is S21, which is minus root EB for binary 0. And similarly, if you substitute here minus root EB, that is x plus root EB square. If you integrate this probability density function, we'll get the probability of error. This is the probability of error when zero is transmitted and received as binary 1. So then 1 by root pi n naught integral 0 to infinity, that is the bound, the threshold. Threshold is 0. Threshold is 0 between. So this is S1 and this is S2. So the boundary is 0. So this is what dik 2 root EB. So this is what root EB energy, this is minus root EB energy. So this is what threshold 0. We integrate this to express in terms of complementary error function. Complementary error function is defined ERFC of u. So the function of u, integral u to infinity e power minus z square, is a decreasing function of exponentially when u is taken. Okay, this is where complementary error function we express the probability of error. So we substitute as we get e power minus z square. So this part is as z square. So that is x1 plus root EB by root n naught. So that is what z. So then dz is dx by root n naught. So then integral e power minus z square dz dx is dz into root n naught. So that is what integral e power minus z square dx is dz root n naught. So the lower limit is 0. You substitute here 0. 0 if you substitute here x equal to 0, root EB by n naught. So this is what root EB by n naught is the lower limit. And an x equal to infinity, upper limit becomes infinity. So this is already 1 by root pi n naught is already here. It is there, and this root n naught and root n naught gets cancelled. 1 by root pi integral root dv by n naught to infinity e power minus z square dz. This is similar to complementary error function. So that is equivalent to half complementary error function of u root dv by n naught. So this is energy by noise. Energy by noise. This is equal to ev by n naught. ev by n naught is a signal to noise ratio SNR. So the probability of error of binary 0 when 0 is transmitted received as 1, binary 1. So that is P 0. Similarly, if binary 1 is transmitted, you will receive binary 0. Then that is also by probability of error, P1E. P1E is the probability of error similar to P0. Here the mu, which is the mean, S12, S1, S11. S11 is the 2TB. So that is what we derive the similar way. We get half complement error function of 2TB by N naught for binary 1. If you take both, the average of the P0 and P1 is the total probability of error. So you will get again this plus this divided by 2, you will get the same half complementary error function of 2TB by N naught. So this is where the complementary function of 2TB by N naught. So this is where the probability of error of BPSK, which is similar to the equivalent distance in terms of equivalent distance. What is equivalent distance? TAK. TAK is 2 root TB. Substitute here, root TB is TAK by 2. So root TB is TAK by 2. So half complementary error function of TAK by 2 root N naught. So in terms of equivalent distance, TAK half complementary error function of DAK by 2 root N naught, or for BPSK, the half complementary error function of root EB by N naught. So EB by N naught ratio. So if EB root EB, the energy per bit is more, then probability of error is less, because it is complementary error function. It's a decreasing function, exponentially decreasing function. Having more distance between binary 1 and binary 0, or signal between the equivalent distance between two signal vectors DAK, so that is having more energy, then it's a less probable. More energy having less probable of bit error. So that is what, if equivalent distance is increases, then the probability of error is decreases. So that is what the probability of error of BPSK. So it's a well-known probability of error of BPSK is just half complementary error function of root EV by N naught is the probability of error. So it depends on EV by N naught, the ratio of signal energy by noise. Okay, so this is where we come across probability of error, we estimate. Thank you.